Welcome to How to Build a Habitable Planet, Lecture 2. Today we'll be talking about general scientific things. And in particular, we'll be talking about the characteristics of natural systems, because natural systems are the way the universe works. The aims of this lecture are first to convey the importance and difficulty of scale. That's a problem we're going to be encountering throughout the course, as we deal from very small things to very large things, as we deal with timescales of years when we're talking about climate change, to hundreds of thousands of years when we're talking about glacial cycles, to billions of years when we're talking about Earth history. Then we'll talk about the difference between reductionist and systems thinking, and how each of these approaches have an important place in modern science. And for that, to understand the limitations of reductionism, you also need to understand a little bit about chaos. So we'll have some examples of how chaos works. And then we'll develop this concept of natural systems as the way the universe works. Earths, humans, and cells, galaxies, are all natural systems. And natural systems naturally include cycles, feedbacks, recycling, and movement everywhere. So let's first turn to scale. What is the actual size of what is shown in the figure that you see on your screen? This is the hydrogen atom, a single proton and a single electron. The size of the proton and the electron are about 10 to the minus 15th meters. That's a decimal point with 15 zeros in front of it before you get to the 1. We could show a slide of exactly the same size, which is the Andromeda galaxy. It's about twice the size of our own Milky Way. It's 200,000 light years across. That's 2.2 times 10 to the 21 meters. So on the same slide, we can show an electron, 10 to the minus 15th meters, a galaxy, 10 to the 21 meters, a human being, 1 or 2 meters. They're all the same size on the screen, but they reflect entirely different phenomena, differing by factors of trillions in terms of their size. And this human being, for example, which is not very big, 1 or 2 meters, nonetheless, it's made up of 7 times 10 to the 27th atoms, most of which are these atoms, hydrogen atoms. We encounter the same problem when we're dealing with time. Big Bang began 13.7 billion years ago, so universal history is 4 times 10 to the 17th seconds. The atomic reactions that take place inside of stars are in nanoseconds, 10 to the minus 9 seconds. When we're talking about a geological period, we're talking about tens of millions of years. And when we talk about all these things, we're going to be telling stories. We could say the story of the universe, beginning at the Big Bang, 9 billion years pass, and then the solar system forms, 4.5 billion years pass, and 200,000 years ago the first humans appear. Or we can talk about the story of this semester. It starts this week. In a month or so, we'll have a midterm exam. And then ultimately there'll be the final and the holidays happen. This is personal, small. It's represented by a line on the screen. This is universal, unimaginably large, represented by a line on the screen. So in the way we talk about it, in the way the neurons of our brain interact with it, in all these different ways, they seem to be similar, and yet in reality, they couldn't be more different. So this is going to require an effort on your part. We can represent vastly different scales on a page, on a screen in our mind. We see them the same size. We think about them in the same format in our brain, but they represent unimaginably different phenomena. So it's going to require a real mental effort on your part to remember at each moment the scale we are dealing with and to have a feel for it. It takes practice. Well, the classic scientific method is scientific determinism. And while it may have started with the Greeks a couple thousand years ago, well, the first great modern physicist was Galileo. And he carried out a series of very carefully constructed experiments where he did things like roll a ball down an inclined plane, and by changing the height of the plane, he could determine how quickly the ball rolled. And in this way, he was able to generate observational data. Galileo also discovered the telescope, and through use of the telescope, much more precise observations were able to be made of the planets and the stars. Kepler synthesized these data to come up with a remarkable observation known today as Kepler's laws. Those were that planets, in their journey around the sun, map out equal areas in equal times. So when the planet is far from the sun, as shown here, it moves relatively slowly and forms a long, skinny pizza slice, if you like. When it's close to the star on the other side, then it moves much more rapidly and forms a shorter and more stubby pizza slice, but the two slices have exactly the same area. Equal areas in equal times. So here were these amazing observations, but why were they true? And Isaac Newton had the astounding insights to realize that he could explain both Galileo's observations and Kepler's observations with a simple, single universal law, Newton's law of gravitation, representing the force between two objects as representing a constant, g, whose value became determined exactly only much later, and the masses of the two objects divided by r squared, the distance between the two objects squared. Using that law, both Galileo's observations and Kepler's observations of the movements of planets around the sun could be explained. A remarkable achievement in human history, where a simple, single equation was able to explain observations on a vast variety of scales using a very simple principle of gravitational attraction. Now, of course, this is very useful, and the ability to calculate things on the basis of Newton laws leads to very useful observations that we can make, for example, when we're trying to predict whether an asteroid is going to impact the Earth. This is going to be an illustration of a NASA tool, and for you to see it large enough in Panopto, you're going to have to click on the screen expansion button in the upper left-hand corner of the Panopto screen that you're looking at, and then you should see this full screen. What we see here are the orbits of the planets going around the sun, and also we see the orbit of an asteroid indicated by this white orbit, and it crosses Earth's orbit in blue at 2 points. So it's an Earth-crossing orbit, which means that at some point it's going to impact the Earth. So let's move forward in time, and you can see Earth moving around the sun and the asteroid moving around as well. There's one crossing point. They remain far apart. Now we get close to one another. I'll change the time frame so that we're moving every 6 hours. And as we go forward, and now I'll step it forward one step at a time. You can see them getting very close to one another. They're still not at the intersection point. The intersection point is there, and there it's simultaneously together. So that's September 2nd at 4 o'clock in the afternoon. And at that point on this scale, it looks like there was an impact, but in fact, the asteroid passed about 1,000 miles away from the Earth and so did not impact it. This particular asteroid is also small, and so if it did impact the Earth, it would likely explode in the atmosphere and not cause any damage at the surface. But there are other Earth-crossing asteroids which eventually would create havoc and destroy modern civilization. But by the application of Newton's laws, we're able to predict when those things would be happening and keep very close track of them in the heavens. Very useful. Now, there are much more striking examples of impacts, of course, in Earth history, like the extinction of the dinosaurs, but even more recently, like in the early 1990s, when a comet came into the inner solar system, broke up into small pieces, and was captured in orbit around Jupiter. Then it went down in this way. It was first discovered in March of 1993, and then 14 or 15 months later, it impacted Jupiter with all its dispersed fragments, leading to a whole series of scars on Jupiter's surface. So here's the first impact, then you have another impact, then you have another one that you can just barely see down here. Jupiter's a huge planet, so these impacts are having devastating effects on the Jovian atmosphere. If this comet had impacted Earth, it would have been sufficiently severe that it would have destroyed civilization. So sometimes people call Jupiter our protector or our big brother because its gravitational field can capture some of these comets that if they came into the inner solar system and impacted Earth would have disastrous consequences. So deterministic science is very powerful, very useful, has very strong applications that are used in our society all the time. What are the limits to reductionism? Well, the first is that the real world is an open system, not an idealized one. So even in the calculation of asteroids, it turns out it's an easy calculation if you just use the gravitational field of the sun. But when you include the gravitational fields of all the planets, the calculation becomes extremely difficult and so uncertain that you're having to continually redo it to adjust the predictions of the object's orbit. The other thing is that sometimes, even in completely deterministic systems, many natural phenomena exhibit chaotic behavior. So we can illustrate chaotic behavior by making a simple, deceptively simple, feedback equation. So we have this deceptively simple equation where you take a value of x, that's x to the n, and you multiply it by a constant a, and you multiply it by 1 minus that value. That result of that equation is a new number, x n plus 1, and you'll put that through the next cycle. It'll be iterative. You'll take xn plus 1, you'll stick it into this equation, you'll get xn plus 2, you'll put xn plus 2 into the equation, you'll get xn plus 3, and so on, over and over again. So this is a feedback equation because as x gets large, 1 minus x gets small, so the larger factor you have here, the smaller factor you have there. If you look at this, it's ax minus ax squared, and so that's an inverted parabola. This is the value, for example, for a is equal to 2. That's the value for as a is equal to 4. So let's do a simple numerical experiment to see what happens when we do this iterative process over and over again. So I have here a spreadsheet in Microsoft Excel, and if we take a value of a up here equal to 2, and we start with an initial value of 0.5, we'll just stay right there at 0.5. If we started at a high value of, say, 0.9, then even though the value is at 0.9, we very rapidly converge to 0.5. This is what it looks like after 80 iterations. You've just reached a complete steady state. Now what I have here is numbers that are very close to one another for the starting position, 0.9, 0.8999991, and so on. So small variations don't make any difference. You end up with the same value. And even large differences, you ultimately end up with the same value. If I put 0.01 in there, it will take a few more steps, but you reach the steady state. If, on the other hand, I go to a value of 3.5 for A, then you see you're getting an oscillating system where you have 4 different values and you're oscillating between them. If I were at 3.2, you'd have 2 values that you were oscillating between. And so here we are after 80 iterations, and you see you're jumping back and forth between 0.5 and 0.8. So you have a system that has 2 states that it can arrive at. Things get very interesting, though, when you get up to values of, say, 3.9. Now we're looking at these 2 different graphs. This one is based on this value, our starting value of 0.001, and this one is based on the starting value that's just a little tiny bit different, 0.009 with a bunch of other 9s after it. Or if we started at a value of 0.5, This one would be 0.499995. And so you generate this chaotic behavior where you can't really predict what's going to happen. And when you look after 80 iterations, you can see in this case, you can see the pattern that it's following. And in this case, you see it's following an entirely different pattern. Therefore, you can't predict exactly what's going to be happening. If I change this number, the starting condition, even by trivially small amounts, you end up with a completely different outcome. So here's another illustration of what I just showed you with the spreadsheet. Values of A of 2.8, of 3.2, an oscillating system, and of 3.9 when you get this chaotic behavior. Now, you can plot the results of all values of A by plotting A on the x-axis and looking at the possible long-term values you can get when you go through many iterations of this system. So for values less than 3, you end up with a single value. For between 3 and 3.4, you end up with 2 values. When you have 3.5, you end up 4 values. And then you get a chaotic system where you can have any value that you end up with. There's no predictive capacity. You have no idea where you're going to end up. So weather is a chaotic system like that. And this means that you can predict very well what's going to be happening a few hours in advance, not so bad, a day in advance. But as the time increases, you can't know exactly where the hurricane is going to be or how strong it's going to be. So this was the hurricane that Trump famously said was going to be hitting Alabama, but this is the actual weather forecast for it. And whenever you look at hurricanes, we'll probably get more this hurricane season, you'll see that the cone of uncertainty progressively increases with time. That's because of this chaotic behavior of the system. So the real world is an open system, and some equations that govern real systems exhibit chaotic behavior, and this limits long-term predictions and uncertainty. You can imagine the equation that I showed you is a very simple one, very simple feedback equation. You can imagine what happens when you have hugely complicated systems like weather. This is why there's the famous saying, butterfly flapping its wings in China can lead to a hurricane in the Atlantic. Very small changes in initial conditions can lead to very different outcomes. So we just demonstrated using a numerical experiment how some systems can be chaotic. And they get chaotic when the value of A in the equation or the amplitude of the system gets larger. We also saw that once they get chaotic, very small changes in initial conditions can have very divergent long-term consequences. So let's look at that with a physical example that you can actually see rather than just some equation. Here we have two double pendulums, and so you can spin both around this top axis and also around the bottom axis. And if we take these two pendulums and we have a small amplitude and let them off together, they stay very well aligned. As we increase the amplitude, the behavior is a little more erratic, but they stay pretty well aligned. But if we take them to a very high amplitude of variation, they begin together, rapidly diverge, and then have completely different behavior. So we've seen that the idea of having deterministic equations can be very powerful in calculating things like the trajectory of an asteroid. But we've also seen that it has its limitations. In particular, it's limited because many natural systems have chaotic behavior, which means that while you can calculate things perhaps quite well for the immediate future, as soon as you go out in any distance at all, you have a lot of trouble calculating it. The errors get very large and you can't make any predictions. Or if you take something like a garden hose, and you say, I'm going to open the garden hose and predict where the water is going to fall from the garden hose, each drop. It breaks that into a cascade of droplets that are following sort of randomly at some distance from the hose. And no one could be able to calculate exactly where those are going to fall, but when you're there with the hose, you can guide it to be in the right direction where you want it to go and water the plant. And yet, calculating it would be well nigh impossible, even for a supercomputer. The other thing is that the real world consists of systems, not just objects. So what do we mean by systems? In a system, the whole is greater than the sum of the parts. That's because the relationship among the parts determines the characteristics of the system and give it its meaning. And if you break it down, you lose essential aspects that are characteristic only of the whole. So take a human being. A human being has a certain meaning, has a certain significance, has a certain function, has a certain capacity. But if you took a human being and you broke us apart and you laid all our organs very carefully dissected out onto a table and all the bones and everything was there, obviously that entity of stuff lying on the table completely loses the essential characteristics of what it means to be a living being. Or if you take a cell phone has a certain function and it also has certain meaning. All of us have a relationship with our cell phone. Cell phones have significance because they connect everyone all around the world. And yet if you took the cell phone and you very carefully took it apart and laid the parts down on the table, all those parts mean essentially nothing and have no function. They have no significance. They've completely lost their essential characteristics. So we can give a very simple example of that, even by considering something as simple as a straight line. The point of this demonstration is to show you that there is more to life than equations, which you probably already knew. The amazing result of Newton's discoveries was that simple equations could be used to predict the motions of the planets and also the results of Galileo's experiments with inclined planes. So we can write equations for things and they have predictive value. So for example, we can write equations for a straight line, y equals mx plus b, and there's a straight line. And we can have another equation for a straight line, y equals m2x plus b, and that's another straight line. And when these two things are going off in different directions, they have different values of m and different values of b, and their positions can be very exactly presented or defined by those equations. But if you take these things and you just look at it in different configurations, even when you have one straight line, it creates a different impression as you see it. If it's vertical, if it's horizontal, if it's 45 degrees, or if it's just slightly off vertical. It's different when you look at it. It creates a different impression. Now, if you take this straight line and you put it in movement, so it goes around like that, or it goes like this, that conveys very different information than the straight line itself, even though you could define all the movements of this object with a series of these equations. Now, when you take two things and put them in relationship with one another, two straight lines, when they get in relationship, they also create a different impression that has different meaning for you. So, or if you just look and you see what you're experiencing on the inside, you'll see that every series of positions has a different effect on you. So then we can put them into a series. So that series of straight lines conveys something. 1 plus 1 equals 2. Or we could do or we can get into trouble. This sequence also can have stronger impressions on us based on our cultural experiences. So, for example, if we see this sequence, that has one impression, and this one creates a different impression. All of this is just two straight lines, just the equations of two straight lines. And yet the meaning, the significance that we feel as human beings, that we interpret with our mind and also with our emotions, is far grander than can be expressed in the mathematical equations alone. So we've seen that systems imply a whole is greater than the sum of the parts. And we've seen how relationship matters even for simple things, and of course even more importantly for more complex things like human beings. And that if you break systems down, you lose essential aspects, because these essential aspects are characteristics of the whole and aren't characteristics of the parts separated from the whole. Well, systems is largely the way that the universe works. Some systems we would like to understand, what I call natural systems, are things like this list here, ranging from cells all the way up to the universe. So we can ask, when we look at a list like this, which covers such a vast range of scales, are there properties that all of these have in common? And these would be the properties of natural systems. The first thing is that they are invariably in movement. If you look at ourselves, you see that we're moving all the time. Our sensations are moving, our blood is moving, we're breathing, new impressions are coming in, we're blinking. We're invariably in movement, and this is true of the earth, it's true of the sun, it's true of all natural systems. It's even true of apparently inert things like rocks, where you can see that the movement of the plates, the convection of the Earth's interior, the convection of the atmosphere, the convection of the ocean. Every part of the Earth system is in movement. The second characteristic is that they're sustained by an external energy source, and this energy flows through the system. Everything on the Earth is supported by the energy coming from the sun. Everything in us is supported by the food that we eat. Everything in the sun is supported by the nuclear reactions that take place in the sun, which ultimately harvest potential energy created during the Big Bang. So every one of these systems we look at requires energy and uses energy so that the energy is moving through the system. It's part of movement. Then all systems involve chemical transformations and cycles. So we can look at this in many scales. If we look at ourselves, the blood is going through us, cycling carbon dioxide, taking in oxygen. All these chemical transformations are taking place. We're continually being recycled. Our cells are being replaced. Our lungs are being replaced. Not the lungs, but the air in the lungs is being replaced. So these chemical transformations and cycles are taking place in us every second. And it's true in the Earth as well. You can take any component, water, nitrogen, oxygen, carbon, and it's involved in an Earth cycle. So here's maybe the most familiar example to us, which is the water cycle, that things evaporate from the oceans, they go up into the atmosphere, form clouds and rain. And that rain then causes erosion on the land, goes into groundwater, goes into rivers, goes back into the ocean, and so the water is continually cycling through this whole system on a fairly short time scale. It's true in a more complex way for the carbon cycle. The ultimate source of carbon is carbon coming out of volcanoes. Of course, we're adding carbon to the atmosphere today, particularly in the form of burning of fossil fuels. Carbon is also put into the atmosphere by respiration of animals like ourselves. We take in food, we breathe out CO2, that's part of the carbon cycle. And the carbon forms rocks that are dissolved as calcium carbonate in the bottom of the ocean. And the carbon is cycling through all living things, forming organic matter and having the organic matter breaking down. And if you generally look at the Earth, all these different cycles are related to one another. So as we talked about in the first lecture, you have hydrothermal vents at ocean ridges, cycling the ocean through the rocks, transforming both. The oceans are in contact with the atmosphere. The recycling of the plates creates to the formation of continents that leads to volcanism, which contributes to the atmosphere. The biosphere is interacting with both ocean, atmosphere, and the rocks on the surface through soils. So all of these things are linked together in a highly complex and interactive system. The next characteristic that is perhaps less familiar to us is that systems are maintained in a very range of states. They're in a kind of steady state. But this state is not at equilibrium. You think, well, everything goes to equilibrium. Well, that's one of the forces of nature, but not the only one. Systems are sustained far from equilibrium by energy inputs and by feedbacks. So if you take our bodies, we're at 98.6 degrees Fahrenheit when we're healthy, and our body temperature is regulated. It's not in equilibrium with the surroundings. Otherwise we'd be at 30 degrees on a freezing winter day, and we'd be at 100 degrees on a sweltering hot summer day. We're maintained at this steady state. Whether it's too hot outside or too cold outside, we're far from equilibrium with our environments. So this takes place by a series of feedbacks, that if our body temperature is too low, there's a message sent to the brain. That sends a message to some of our glands. Those release hormones. Cells can increase metabolism and make more heat. If we get too hot, another signal is sent and we start to sweat, and the sweat causes us to cool down. So our body is continually responding through feedbacks to whatever the temperature is externally to us to make sure that our temperature on the inside stays constant. Now, there are two types of feedbacks that are important. One is a negative feedback. You push in one direction and something pushes back. And the other is a positive feedback. You push a little bit in one direction and you get a big push. So a positive feedback is like a trigger. On a rifle, all you need to do is pull a little trigger. And you pull a little trigger and a huge amount of energy is released. A cannon would be even more dramatic example. That's a positive feedback. A negative feedback is you push in one direction and something compensates for it. An example would be sweating when we get too hot. So these two things acting together are what leads to this possibility of steady state disequilibrium, to this homeostasis. So let's consider an example which is familiar to us, namely an oven. So when you have an oven, it's there. You turn on the oven and it's cold. So because it's cold, the thermostat sees it's not at the right temperature and it emits a little spark. And that spark then lights the heating elements or turns on the gas. That's a positive feedback. A little tiny movement from you just turning the dial on the oven causes a big response, namely the turn up of huge gas burners to bring the temperature up. When the temperature gets up too high, the thermostat measures the temperature and it sends another signal which turns off the flame. That's a negative feedback. Gets too hot, turn off the flame, negative. Not warm enough, turn on the flame, positive. A little bit of change can lead to a big result. A little bit of movement can lead to great warming. Or if it gets too hot, you push back in the other direction. And the temperatures can thus be maintained over a very narrow state where we can cook. Stars have a feedback. The gravitational contraction is causing the star to heat up. That makes higher temperatures and faster nuclear fusion. That generates more heat, and that causes the star to expand. The expanded star has lower temperatures, lessening nuclear fusion, and the star starts to contract. So you have these two feedbacks, one causing the star to expand, the other causing it to contract, two opposing forces. And this allows the star to be in its steady state, very far from equilibrium, at very high temperatures, and the temperatures of outer space are extremely low. So the star is maintained at this steady state. Sun looks more or less the same to us every day, but very far from equilibrium, from the space in which it inhabits. Climate is another example where you have a complicated set of feedbacks, and that feedbacks involves all the components of the Earth system. The ultimate source of CO2 to the atmosphere is volcanoes. So you're melting the Earth's interior, you're dissolving the carbon dioxide that's in the Earth's interior, and it's degassed when the volcano erupts. That adding CO2 to the atmosphere then causes global warming, and as the CO2 rises in the atmosphere, the temperature of the Earth heats up. The counterbalancing effect is the deposition of carbonate rocks at the bottom of the sea floor. The carbonate rocks in the bottom of the sea floor are made up of calcium carbonate, CaCO.CO2. That's removing carbon dioxide from the system. So we have inputs, CO2 coming out of volcano, outputs, CO2 being sequestered into rocks in the bottom of the ocean. So how does this feedback work? As the CO2 increases for whatever reason, that leads to increased temperature. That increased temperature, and it's a little tiny increase, leads to a positive feedback because it causes more water to dissolve in the atmosphere. Water is much more abundant than carbon dioxide in the atmosphere, and it's also a greenhouse gas. So the CO2 leads to a positive feedback with water. That leads to much more extensive amounts of warming of the atmosphere. Now we have an enhanced greenhouse effect. The temperature is higher in the atmosphere. There's more rain. The rain has more carbon dioxide in it, and that makes carbonic acid, which makes the rainwater weather more. And so all of these combined lead to enhanced weathering. This enhanced weathering breaks down the rocks and sends calcium ions into the ocean. The calcium ions in the ocean grab up a molecule of CO2 and deposit it as this rock, CaCO3. So you have a positive feedback, high CO2, increased greenhouse gases, more warming, enhanced greenhouse effect, but that then leads to a negative feedback through weathering. If you remove too much CO2 from the atmosphere, the temperature goes down, weathering stops, the CO2 increase from volcanoes is not moderated by the weathering cycle, and so CO2 goes up and the Earth warms. The climate is kept at a really stable temperature over time scales of tens of thousands to hundreds of thousands of years. The next thing is that the natural systems change with time. There is creation, long-term evolution, and ultimately death. And they contain and are nested within systems at smaller and larger scales. So when you look at the list of these galactic entities, all of which are systems, you see that every one of them is related to systems larger than itself and contains within it systems smaller than itself. So the Earth is related to the Sun, and the Earth has within it its water cycle and its ocean and its atmosphere and its crust and its ecosystems. And the ecosystems have within them individuals, such as ourselves. And the individuals are related to the much larger ecosystem of which they're a part, and ultimately to the earth and to the sun, and also contain within them cells, both the eukaryotic cells that are larger and make up most of our organs, and the prokaryotic cells that live within us and are our microbiome. If we look at Earth as a system, all parts of the Earth are in movement. Every Earth component is involved in cycles. These cycles are interlinked and have feedbacks with one another. Every part of the Earth system is a steady state far from equilibrium. On short time scales, that's millions of years. On longer time scales, the Earth system evolves. Earth is related to the larger solar system and to the smaller biological and geological systems of the planet. Earth had a time that it formed 4.5 billion years ago. It's gone through a process of planetary evolution where it changes on the scales of tens of millions to hundreds of millions of years, and ultimately it will end. Each one of us is a system. All parts of us are in movement. Every part of our body is involved in cycles. The cycles are interlinked and have feedbacks with one another, and so we live at a steady state, far from equilibrium on short time scales. But over years or decades, we change. We grow, we become adults, our body seems to get better and better, it reaches its maximum efficacy at around your age, and then starting in a few years, the body begins to decay, and ultimately it dies. Each of us is related to larger systems, the human community, ecosystems, the planet, and to smaller systems, organs, cells. Each of us had a time of origin, our birth. Each of us ultimately will die. So in this sense, there are these common features. Each of us shares common features with the Earth, with the sun, with the galaxy, with cells, with other organisms. All of us operating in this fundamental way of natural systems, which seems to be a characteristic feature of our universe. So the take-home points from this lecture is first, to try to always be aware of the scale of the phenomenon we're talking about, the scale of size and also the scale of time. Determinism is very important, very scientific. It has its place, but it does not describe much of the real world very well. Many real-world systems are chaotic, and chaos is non-intuitive. No matter how closely you maintain the initial conditions, in chaotic systems, eventually they diverge to completely different outcomes. Systems acquire meaning through relationship, and the whole is greater than the sum of the parts. You can't break it down just to a series of equations and have the characteristics of the whole. Natural systems on all scales throughout the universe share a set of common characteristics. I've listed some. Can you think of others? You, me, and the Earth are two such natural systems.